Let's move on. Okay. So can you see guys from the Zoom?
Yes, it's a screen.
Yes. Okay. Thank you. Thank you. Okay. So I'm now recording, right? Okay, I think it's recording. Okay, let's move on. So data augmentation. So now this is more about Bayesian way of handling missing data. So remember the prediction or imputation is to generate, right? Generate missing data given the observed data. The problem is it depends on unknown parameter. So eta, right? So eta is unknown. So you cannot really generate it because you don't know the parameter. So you have to do something. So two different approaches in statistics. One is you average out, you integrate out over unknown parameter. So that is the Bayesian approach. Frequentist approach is to use plug-in. Okay, plug-in because you don't know the parameter. So you plug in to the constant estimator, something like MLE, plug in, and then the conditional distribution is known, right? Then you can do something. So there is the two different schools has different ideas. So now we'll just briefly talk about Bayesian approach to imputation. So again, the goal is to generate missing data from the predictive distribution, right? So prediction model or predictive distribution, the same concept. And now Bayesian, right? We are talking about Bayesian. So Bayesian idea is to use this one. So average over, so average out over the conditional distribution given the data. So that is actually expectation. So then this expectation here refers to with respect to the posterior distribution, right? So then this guy is a limit, probability limit of what? Of k equal to 1 to m p y miss given y observed delta eta star t k. I'm sorry. So what am I doing? What I'm doing here is that delta eta k, where eta star k is a sample from distribution of the partial distribution. Because this probability, because by the law of large number, right, the expectation is a limit of the sample expectation, sample mean. And then this is just the quantity, some function of eta, right? This guy is just a function of eta, and we are taking the expectation of this function of eta. So then this is just a sample mean, right? This is a population mean. So sample mean of this sample mean, and then this sample is generated from this expectation, right? From this distribution, which is the posterior distribution. So then it's actually two-step procedure, because step one, you generate eta. Step two, you generate y miss, right? And then you do it several times and then average them over. So generate eta, and then given eta star, generate y miss. So because this is given, right? This is from step 1. And now the second step seems to be easy, right? The second step is relatively easy because you know this one already as a function of eta. So the step 1 is actually more difficult. So then the real question is how to do the step 1, right? So sometimes, we can name it posterior step. Step 2, imputation step. Or prediction step. Right? Step 1, posterior step. Step 2, imputation step. So let's move on to how to do the posterior step. So the posterior distribution is this one. So if you remember, this is just this one. Okay. So posterior is, remember, posterior is a prior times likelihood, right? So this is a prior. This is likelihood or density, right? Density. And then denominator is just integrate out over the unknown parameter. So denominator is just the normalization. Okay. And then, so that's the first equality. Second equality is what? Second equality is what is the likelihood? So the likelihood is actually a marginal likelihood, right? Marginal density. Marginal density of the observed data, and the joint original one is a full model, right? Full model specification. So you actually integrate out over y miss. So then the whole thing. So then you are actually you can view the numerator. So you can view the whole thing here. Oops, sorry. So let's use, and then so we can call this as a joint density of, right? Joint density of y delta and eta. And so denominator. So then this is joint density and denominator is the marginal density. The denominator is the marginal density of y, obvious, and delta. Denominator. So then this guy is equal to this guy. So remember, in Bayesian, everything is random, right? The parameter is also random. So it's just another random variable. Eta is just another random variable. So we actually have 4 random variables. Or to be rigorous, y miss, y ops, y miss, delta, and eta. So we have 4 random variable. So that's why we have 4. 1, 2, 3, 4. Okay. So 4 random variable, but we conditional on what? Conditional on y obs and delta, marginal density of the y. So then what is unknown is eta n, right? So it's really just the same same thing, but it's just a different way of writing down the same thing. So okay, so the partial distribution is a marginal integrating out the joint partial distribution. So we can call it joint posterior. Well, that is not real. So okay, let me back up. So I guess better way is to first investigate what these actually mean. So here we have four of them. These two are always observed. And then the other two is missing or just unknown. So this is known, right? Observed or known. So it's just it's kind of unknown, even known. Right? So we just put the unknown in the left side, which is y miss and eta, and put known in the right side, which is y observed and delta, right? But the problem is that the unknown has two components, right? Y miss and eta, right? We have two different unknown. So we have a different name. So that if you are interested in focusing on eta parameter, we call it partial distribution. If we are interested in missing data itself, we call it predictive distribution. So combining the two, this is just y miss and eta given y obs delta, right? So that is called posterior predictive distribution. Very simple, right? Because it's just a combining posterior distribution and predictive distribution jointly. So that is called the posterior predictive distribution. So we wanna. So this is what we want to generate. I mean, sampling, right? You want to do the sampling of distribution, and then once you sample that, then the marginal, right? Marginal of each is just integrating out. So the real, the main advantage of Bayesian approach is that computing the marginal from the joint is really easy because it's just you generate everything and then just compute the marginal mean, and that's it. That's very simple. In the free contest, it's difficult because you have a profile, and then remember that if you have a profile, then it's not really a likelihood, right? But Bayesian, it's just a simulation and then compute them. So because in Bayesian, everything is integrating out. So then that conceptually very easy. However, there's some. So then the real computational tool is that how to generate this distribution when you know the conditional only. So the idea of keep sampling is that we want to generate the joint distribution from full conditionals. So what do you mean by a full conditional? The full conditional means so if you are interested in generating x1, you leave everything else as given. Okay, if you are interested in generating x2, you basically exclude x2 and everything else in the right side. Okay, so that's, and then we keep doing, right? I mean, we iterate. So that is the basically idea. And then some details. So then, I mean, the idea itself is very intuitive, right? I mean, you just generated conditional distribution. So because in this case, the left side is a univariate. So univariate sampling is easy, usually, right? And everything else is conditional. So univariate sampling is easy. But the question is, the first question is that we only use the full conditional distribution to compute the Gibbs sampling. So then you may wonder, are you saying that full conditional determines the joint? That's not always true. So the question is, do the full conditionals fully specify the joint distribution? The answer is no, but sometimes yes, right? So the question is when we have the yes. So that is the one question. And the other question is it converged to something? You know, we have a ergosity in the end. So that is the another question. So invariance, remember the invariance is the stationary. So then so does it really converge to stable distribution in the end of the day? So that is the second question. So this whole covering of this topic is beyond the class, beyond the focus of the class, but I will briefly just mention some key concept. So the first question, to answer the first question, it is called the Hammersley-Clifford theorem. The Hammersley-Clifford theorem basically says that your joint density, right? Your joint density is a product of the full conditional ratio of the two full conditional density. Looks very weird, but anyway, you have a weight, right? Yeah, so this theorem basically gives us a set of conditions that we can achieve that the answer to the first question. So there's some, you know, conditions like a positivity condition. So there's some technical conditions, but let me try to understand. So let's this formula looks very hard to digest. So let's use a simple, more simpler example to see whether we can figure out the meaning. So the justification for P is probably not really difficult. So we just use some basic, you know, probability algebra. So here, joint density is a conditional density times marginal, right? So that's no problem. So now, okay, for any point, so this is the, so here x1, x2, x3 is a random variable. I mean, they can change, but let's fix a particular number, okay, in the support. So support is the positive mass, right? So in the support, so because this is equation 2 holds for all, right? For all x1, x2, x3 in the support, so it should satisfy a particular, you know, is it a C? How can I pronounce it? C, zeta, 그 사이? 응? 컷이. See? Okay. See, okay. Psi. Well, whatever it is, this is right. I mean, not difficult, just the change. And then turns out, then you can actually play, right? Play the algebra and then write this way. Then the right side. So we know that this is free of psi 3, right? So that means the right side you have a, so even though it's a function of psi 3, it is not actually. Okay. But and now we plug in to here. So we plug this into here to get this. Right? So then okay. So then equation 3 basically means you're able to relax this x3 by some constant and then make an extra term to get equation, right? So that although this is joint, x1, x2, x3 is actually, they are related, you are able to move it to write it as a conditional distribution. So this expression, the bottom line of this expression is the original property in the joint distribution is now changed to the property of the conditional distribution. So you can do the same thing. Because so this is joint. This is in some sense marginal. It's not really marginal, but you remove, right? You remove x3 to make it more like a marginal, right? And so then this is still conditional, but the denominator is the extra, extra term to make up for this change, right? I mean, so you can understand that way. That means you can now don't worry about this, right? And just view it as a condition joint, right? You have a joint, and then you marginalize, and you write it conditional, and denominator you pay the price, right? And so that if you do that, end of the day you get this. So you have a constant, you have a marginal, and so you have a x1 and then x2 given x1 and then x3 given x1 and x2. Okay. So then once you write this form, see what is interesting. So this is really a constant, right? You don't have to constant. So you don't have to worry about that. But the other factors are just 3 full conditional distributions, right? So this is the full conditional of x1 given x and x2. This is full conditional of x2 given x1 and x3. This is a full conditional of x3 given x1 and x2. So this is really clever idea. And so yeah. You mean this one? The wider ratio is the I think so we have a margin, okay, joint equal marginal times conditional divided by the penalty, right? I mean some price. And then the denominator is exactly the same form as the numerator, but you just reflect the change.
question is that in that first ratio, can we take the denominator as like proportionality constant?
You mean the denominator?
Like 2 given psi 1 and psi 2.
So your question is, can we just ignore the?
No,
Well,
not
actually, you have something here, right? Okay. So yeah. So- Huh?
Those are constantly, right? So the conditional of the first ratio, the denominator of y is not constant.
So this is constant.
Oh, this is not.
This is constant, right?
Okay.
So I'm
The
not.
numerator only is the marginal, right?
Yeah. So yeah. Well, the if you look at the theorem here, so j equal to, for example, j equal to 1. That means the denominator is constant. So theorem itself is correct. I mean, okay. And the point is, really, each component is just full conditional. I mean, but you have a sequentially, have some x part, some psi part, but so okay. Well, okay, let's move on. So we have here's an example. Suppose we have this model. X1 given X2 is an exponential distribution with mean x lambda 1, lambda x2. So then the density here is what? You use so that the density function is actually lambda x2, okay, but you have a psi 2 x1, okay. So this is density. This is constant. So you don't have to work constant. And then this guy is what? This guy is exponential of minus lambda. So x2 given x1 is lambda x1 and then psi 2. So actually, see, in this case, you have a cancellation. So the only thing left is this one, exponential minus x1 lambda x1 x2. Okay. So you have, so end of the day, you have, so this is constant, this one cancels with this one, and so end of the day, you have this one. So then if you do that, this integration is infinity. So the point is here is that one just caveat of the Hammersley-Clifford theorem. The Hammersley-Clifford theorem does not say that conditional. So the assumption is that actually two assumptions, right? One assumption is that joint density satisfies the positive condition. The second assumption is that the joint density exists. Okay. So if the joint density exists, then it has this equivalence. Okay. This example is an example where the joint density does not exist. Okay. So don't get, so that means this is not really this is not really correct. So that's why so in this exam case, Hammersley-Clifford theorem does not hold. So because the joint density doesn't exist. Okay. So well, I will skip this part. Basically, under some nice conditions, the Gibbs sampling satisfies the this property, ergodic property, and you have some conditions, but so for example, something like positivity conditions and invariant condition. But I think this condition is fairly weak condition actually. And here's one example. This is a fairly simple toy example. So if you basically well, nobody really used this approach, but anyway, you can, if you are interested in generating x1, x2 from a bivalent normal distribution, you can actually apply Gibbs sampling, and so conditionally, the conditional distribution of the normal distribution is normal, right? So that it's easy to generate. So it's fairly easy to generate your sample. And so if at some point it'll converge to stable distribution. Okay. So notice that this, okay. So in the Gibbs sampling, they are dependent, right? So correlated, usually positively correlated. The amount of correlation increase with the dependency of the components. Okay, so the point, so here we are talking about two different correlations. So the correlation across T and the correlation within the Gibbs sampling. Okay, so they are actually, so one increase, the other one decreases, something like that. So the one consequences is that the Gibbs sampling, because of the positive correlation, usually it's not really efficient, right? I mean, if you have a correlation, then you increase the variance. I think that is one consequences. Okay. Now let's briefly discuss how the Gibbs sampling. So Gibbs sampling is general tool for MCMC sampling, but now we will focus on in the context of imputation. Okay, so the data augmentation is an application of the Gibbs sampling to missing data problem. Okay, so then here's so the setup. We have observed data is Y observed and delta. Complete data is Y and delta. So that means Y is Y observed and Y miss, right? And model parameter is eta. So predictive distribution is, and so remember we have two things. So predictive distribution and partial distribution. So this, so you can see that this is, so you have a, okay, we have a 4 component. Remember, in the context of mixing data, we have 4 component, right? Y observed, Y delta, and Y miss, and eta, right? And we are, our sampling problem is just either sampling of Y miss and everything else, or sampling of the eta, everything else. So this guy is this guy, and this guy is this guy. And then this guy is actually this guy. And this guy is actually this guy. So that means what? You generate y is from here. So okay. So this is actually explains Gibbs sampling in the end, because this is full conditional. So this is a full condition of y is, and this is a full condition of eta, right? And then the theory of Gibbs sampling basically says that you can actually, end of the day, you generate a joint simulation of y miss and eta. That is the Gibbs sampling, right? But it perfectly matches with the missing data problem, because you can basically, so you don't have to worry about this one, because you use the previous chain to here to generate. So what I mean by this, so the expression, okay. The expression here means that you use the generated one to plug in, right? Otherwise, so this is given. This is so the first two components are always known, right? The first two components are always known. The only thing unknown is eta, right? But you use the previous sample, right? It gives us, Markov sample to plug in to obtain the update. And then that one is actually plugged in here. So same story here, right? This guy is plugged in here to generate eta. That's exactly the Gibbs sampling structure. Okay. So basically, this Practice expression looks very complicated, but end of the day, we just do this Gibbs sampling. So through imputed value, which is I step, imputation step, and then plug in to draw eta, right? That is the posterior step. Okay.
So with this algorithm, so this is just Gibbs sampling.
Gibbs sampling, right?
So with this algorithm, let's say if I want to approximate the expectation of y is given, so we have predictive distribution, and let's say I want to approximate, let's say, expectation of y is given y observed delta. Then I will use the I-step sample to do some Monte Carlo.
Exactly.
Right.
And
ignore the other one,
ignoring this one. So that is actually idea of multiple imputation. So the idea of multiple imputation is basically you don't have to. So this is actually kind of intermediate thing to get imputed value, right? But end of the day, you can just use this sequence as the final realization from the the predictive distribution. Okay. So this is actually quite interesting. And if you think about the connection between EM algorithm and data augmentation, so there's some similarity, right? Like EM, you have a so what is the E step? What is the M step. So P step is updating your parameter. So that actually matches with M step, right? Then I step is updating, computing the integral, which is actually computing the conditional expectation, right? So expectation of missing data. So that actually is I corresponds to I step. But it's not the same way, right? Not the same way. Actually, so here's a good interpretation. So the I step corresponds to E step of the EM region, okay. And then so these are actually I step and E step are actually quite the same, essentially, because if you think about Monte Carlo EM, right? If you consider given the parameter, you just draw Monte Carlo sampling and then compute the conditional expectation. So the I step and E step are very similar. I mean, essentially the same. But the parameter update step are different. Why? Because in the EM algorithm, the parameters are updated deterministically. Okay. So that means what? You can actually check the convergence. So you use epsilon, right? If you program it, you have a sequence of the theta hat, right? As a from the iteration, and then you use epsilon to determine the convergence, the pointwise convergence, right? However, you never really check. You cannot really check the convergence of the data augmentation because you are actually generating a distribution, samples from distribution. So you never really can use epsilon to check. So how you can check the convergence is much more difficult in the data augmentation language. And actually you can easily get mistaken because it's difficult to get mistaken if the set head is converges, deterministically, right? Update this. You can always, because if they converge, then they will, no matter how small you epsilon, it'll go there, but not the data augmentation. So that's one caveat. But here's a big advantage is that the uncertainty in the possible estimation, parameter estimation is automatically captured in the Bayesian framework. So that's actually what Bayesians are really proud of, because this data augmentation actually gives the uncertainty of the parameter so that the posterior step distribution. So two uses of so you can use this I step to obtain the marginal distribution of the missing data, right? So then you can use that to construct the imputation. Also, you can use the posterior distribution to evaluate the uncertainty of the model. So that actually gives you can either automatically create the confidence interval and things like that. Bayesian confidence, credible regions, whatever. Okay. In the monotone missing pattern, the iterative algorithm is not necessary. It's the same story. So remember, in the monotone missing pattern, in the frequentist approach, we use factoring likelihood approach, right? We use compute the marginal, you factorize, right? Marginal distribution and conditional distribution, and then use the marginal data to estimate the marginal parameter, and then, right? And then you don't have to iterate. Same story here. So here's an example. Okay. So this is a toy example, but let's take a look. So Y is Bernoulli, P is beta, alpha and beta known. Okay. So if we do, so this is actually univariate. So it's, but Anyway, so how, two ways. Method one, how to generate. So imputation, we are interested in imputation, but to do imputation, we have to generate parameter first. Okay, so the parameter distribution, so posterior distribution is this one, method one. Generate posterior probability, right? Generate the P from the posterior distribution, and then from P star, we generate Y. That's one, method one. Method two, which is more computational way, but it's directly related to the data augmentation. So if you use the spirit of the data augmentation, you can actually do, so you generate Y given P, you generate the P given Y, essentially. Okay, so given P, you can generate Y from variable P, and given Y, you can generate P from beta distribution, right? This is the usual. You have a, what is this? This is more like a, you have a likelihood is, you have a P summation Yi 1 minus P summation N minus Yi, right? Summation Yi. This is the likelihood part. And then prior is alpha minus 1 minus P beta minus 1, right? So then likelihood times prior becomes a posterior, which is actually P to the alpha plus summation Yi minus 1 minus beta minus P, and sorry, I don't have a space, but beta plus N minus summation Yi minus 1, right? So it's a very simple Bayesian. So you have a P, you have a likelihood part, you have a prior part, which is the posterior part, which posterior itself is a beta distribution. So that is a conjugated, nice prior. And so because it's beta, basically this is, right? If you know why, then we already know that the posterior distribution is beta distribution. This one. So you can iterate. And then what I like is you use, that's my, as in the homework, I can I can give you two ways of solving the same problem and check whether they are equal, right? So I'm going to do the same thing here. So, okay. Well, this I already covered. So this is already covered here, right? So equivalence of two methods. Basically, well, okay, it's not really long. So let's just quickly go through. So, okay, here's the idea. So if I so this is actually so this is two. It's like this. So posterior step, the inside is a posterior step, and then outside is just okay. So the inside is this one, right? So then what is the posterior mean of P? Posterior mean of P is this one, given the imputed data, right? Because the what is the mean of posterior mean of P? You have we know the beta star distribution, right? So alpha star plus beta. So posterior mean of P given Y1 to Yn is what? N plus alpha plus beta summation I equal to 1 to N Yi plus alpha, right? So we want to use that. Okay, so we use that, but we don't know Yi. But we do know the imputed Y. right? So then we have this one. So this guy basically get this one. So then you can kind of do algebra, right? So you can write it this way. And then lambda is just this one. So if you do that, then so then this is actually Markov, right? You have a Markov chain. So you have a transition, right? From t to t plus 1. So you can actually write it, the conditional expectation, as something like this. And then this is like a sequence, right? So then you can take the limit, but this lambda is less than 1. Okay, so this lambda is less than 1. So you take you have an initial point, and then I don't know. This is a recursive formula, right? And this is a closed form of formula. You know you know what I mean? The sequence, right? The sequence can be defined as a recursively. So the relationship between the previous one and the end of the day you can write. This is so here is from t to t plus 1, while this is from 1 to t plus 1. And then you leave t goes to infinity. Let t goes to infinity, then this second term disappear because lambda is less than 1. So then end of the day you get a0, which is this. Which is exactly, so this is what? This is actually expectation of the P given y12, yr. The method 1. So what is the method 1? Method 1, you have this one, right? You just ignore the missing part and just apply the Bayesian approach to the R observation. And that's what you get. And that actually, so in the limit, what I showed here is that in the limit, they are the same. Okay. So I think that's it. And I already covered this parameter simulation and multiplication. And I have one more example, but I will maybe do it next class. Okay. Okay.